And we're effing live.
Oh.
No, FN, like force.
I'll live with it. I had a couple of videos that I was going to show you, but I just realized I showed them to you earlier. Yeah. The inertia, why the Earth spins, where they had that big granite Earth on the fountain, and some of you, as good, I showed you earlier, because a few of you ran into them over your Christmas break, and that was fine. So we're going to jump right in. Universal gravity. Gravity is a force that exists between Earth and other masses. Actually, gravity is a force that exists between any two masses in the universe. Any two masses in the universe are tugging on each other with a force that we give the name gravity. Okay? So the diagram below shows two masses. Big M, let's think planet, and little m, let's think moon or satellite. So M is the greater mass. Big M is the greater mass. Compare the gravity forces on the two masses. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So I wrote down here, the force exerted by big M, the planet, is greater. Or B, the force exerted by little m, the satellite, is greater. Or C, the forces are the same. What do you think? I've just told you that masses tug on each other. All masses tug on each other. That's the law of universal gravitation. So, does the planet tug harder on the satellite? Does the satellite tug harder on the planet? Or are they both the same? Who says, hey, Dueck, the planet tugs harder on the satellite? Come on. No one. Who says, B, hey, Mr. Dueck, the satellite's tugging harder on the planet? One. Who says, hey, Mr. Dueck, the forces are the same? Convince me. You can convince me with one name and one number, sort of. Yeah? Newton's third. What was Newton's third? Okay, that means if the Earth tugs on the moon with, I'll make up the number, 1,000,000 newtons of force, what does the moon do? Tug on the Earth with exactly 1,000,000 newtons of force. Yeah? It is a slightly unbalanced. Now you're talking about how orbits work, and it does turn out that there's a slight precession, and the moon is closer or further by a couple of inches a year. I can't remember which. I have to go look it up. But it's not. The moon is not quite in a stable orbit. It's close. And part of that is because of how we believe it formed. So we believe the moon formed. Our Earth is around 4.5 billion years old. And we believe around 4.2 billion years ago, when much of the Earth was still liquid, it got slammed into by a planet about the size of Mars, we think, shooting a whole bunch of debris off into outer space. And that debris coalesced into the moon. That's why the rocks on the moon look so much like the rocks on the Earth, because they came from the Earth. That was a surprise to us when we went and landed on the moon and we were looking at the rocks. These aren't that different. We need an explanation. And so that's our current thinking and explanation. We're due for another big asteroid hit. So who knows? This could be the blink of existence in the universe 1,000 years from now. We had a huge asteroid hit Russia last year. Now, it wasn't that big. So in answer to your question, yeah. But as our explanation, sure. Newton's third. Forces come in pairs. The Earth can't tug on a satellite without the satellite tugging back on the Earth with exactly the same force. Or, let's be more specific, the Earth can't tug on you without you tugging back on the Earth. Why do you feel it so much more than the Earth does, though? Well, F equals what? ma. Who has a bigger mass, you or the Earth? So the Earth, such a huge mass, has essentially zero acceleration. It's not, but it would be, doing the math quickly in my head here, it would be, I think, around 21 zeros before you hit your first non-zero digit. So 0.0000, 21 zeros, and then you'd have it's essentially 0. Oh, and the odds are on the other side of the Earth counterbalancing you, there's probably someone of about the equal mass anyways, canceling you out. Cavendish and others since him have designed ingenious experiments to measure this small force of attraction between masses. Small force of attraction, Mr. Dueck? Yeah. They found, come back, don't. Cavendish and others found that the force of gravity, the universal equation, varied inversely with the square of how far apart the objects were. D squared was on the bottom. And they found that it varied directly with the product of the masses, m1 times m2. If you have two masses and you want to find out the force of gravitation between them, the force of attraction between them, they found, oh, I need to multiply the masses on top. I need to divide the distance between them squared on the bottom. Except this equation didn't quite work. You needed to add some kind of a constant to make the numbers work. What do you mean by that? Well, they said, I know the equation is this, but I need something right there so that I end up with newtons. Because right now I have kilograms squared per meters squared, which is not newtons. And this constant, as it turns out, is really, the number that goes there to make this work is really small. Really small. They found this. Here's Newton's law of universal gravitation. Fg is equal to, so m1, m2 over d squared, or if they're moving in a circle, instead of d, we'll often use an r for radius squared, but how far apart they are. And we put a capital G there. That's called Newton's universal gravitational constant. That's the number that we have to put there. The same way as if you want to convert from meters to kilometers, what's the constant? You multiply by 1,000. The same way as if you want to go from degrees Celsius to degrees Fahrenheit, it's times by 9 divided by 5. The same way, we do conversions all the time. The same way if you want to go from minutes to hours, what's the constant? If you want to go from minutes to hours, what do you have to multiply by? 60. If you want to go from kilograms per meters squared and end up in newtons, you have to multiply by that number G, except it's really small. What is it? It's 6.67 times 10 to the negative 11. And this is what took them a while to actually measure. It's 6.67 times 10 to the negative 11. It's 0.00000000000667. Oh, and its units are Newton meters squared per kilogram squared. I don't care about the units. It's just that's the number that you have to put there for this equation to work. The same way as if you want to go from minutes to hours, you better put a 60 in front of the minutes. The same way if you want to go from meters to kilometers, you better put 1,000 in front of the... Or sorry, if you want to go from kilometers to meters, you got to put 1,000 in front of there. There is the constant. It's just not a nice metric constant. Sorry, the universe doesn't cooperate with us all the time. This is Newton's law of universal gravitation. F equals big G, m1, m2 over d squared. So example, calculate the force between two 4-kilogram masses separated by 0.5 meters. Okay, I can do this. Equals big G, m1, m2 over d squared. And you're going to need your calculators out. Where big G, this capital G, by the way, little g, 9.8, that's the one here on the Earth. This is the one that works on any planet, anywhere in the universe, wherever you go, and it is 6.67 times 10 to the negative 11. How big is mass 1? How big is mass 1? 4 kilograms. How big is mass 2? Also 4 kilograms. Divided by, how far apart are they? 0.5 squared. If I had a 4 kilogram mass right in this hand and a 4 kilogram mass in this hand, and I held them about a half a meter apart, there is technically a force of attraction between them. They are pulling on each other with the force of gravity. How big? Not very. Crunch the numbers, what do you get? This is also a time for you to remember where your scientific notation button is, because you're going to be using it now. In other words, try this along with me. And I find a force of 4.27 times 10 to the negative 9 newtons. See if you get the same thing. Is that very big? No. No. But it's there. It's there. We'll come back to that, but here is Sir Isaac Newton's law of universal gravitation. Okay? So we've looked at how this all fits together. Screen is still frozen. Thank you, thank you. So we looked, and there was our answer when we calculated between two 4 kilogram masses. There is a force in newtons. It's 0.00000000427. I mean, yes, we have instruments that can detect it. Certainly a human being could not detect that with their bare hands. Or, as the illustration that I did, all of you right now are exerting gravitational force on each other. You don't even notice it. It's small. Gravity is a very, very, very small force. You need a huge mass before you notice any difference. Now, going back to Anthony and Zach, it is true. Let's suppose they were in outer space. Let's suppose there was some dire accident and you were outside the space shuttle and the space shuttle blew and you're just floating there. You would very, very gradually, slowly be pulled towards each other. It would take a while because the force is not big, but because there's no other forces acting on you, you would slowly, eventually come together. That's what's happening all the time with planets and asteroids and orbits and things on the cosmic scale. Hey, let's find the force of gravity between the Earth, which has a mass of 5.98 times 10 to the 24th kilograms, and the Moon, which has a mass of 7.35 times 10 to the 22 kilograms. Oh, and the distance between the Moon and the Earth is 3.84 times 10 to the 8th. What do they want us to find here, Jeff? What do they want us to find here? Calculate what?
The orbital radius.
No, start reading at the beginning. Calculate what?
The force of gravity.
Stop right there. Now, we're not going to use mg because we're not on the Earth. We're going to use our new equation today. Big G, m1, m2 over. Traditionally, when you're talking between planets, because the Moon orbits around the Earth in a circle, we use an r for radius instead of a d for distance. And I'm probably going to do that without thinking about it. So the r and the d are fairly interchangeable in terms of units, but I'll just do it right because I'm a nerd, Emma. Okay? Hey, let's plug and chug. What was big G, this weird gravitational constant? It's on your formula sheet as well, so you don't have to memorize it. It was 6.67 times what? Times 10 to the negative 11? Mass of the Earth, 5.98 times 10 to the 24th. Mass of the Moon, 7.35 times 10 to the 22 divided by 3.84 times 10 to the 8th squared. you want to practice figuring out, because this is a very complicated equation, how you type this into your calculator. In particular, you want to find out how your calculator does scientific notation squared in the denominator. So get your calculator out. I'm deliberately not typing because so many of you copy. I'm going to freeze the screen, and then we'll see if we get the same answer. But try and type this on your own. You need to figure out how this works. I think you get something times 10 to the 20th. Almost exactly 2, but not quite. A little bit low. Okay, so if you're doing it right. Now, on my calculator, when I square scientific notation, I don't have to use brackets. You might have to put your scientific notation in brackets with the squared outside the brackets. I don't know how your calculator works. But this is a fairly big force. So, show me your calculator. Hand it my way. You forgot the squared. And now your answer button, unfortunately, is wrong, so you got to go from scratch. It's 3.84 times 10 to the 8th. Squared! Now I'll come help. So, let's do some thought experiments. Turn the page. We're going to see if we can wrap our brain around the mathematics contained in Newton's equation that helps explain how outer space works. So I wrote here, if the force of gravity between two equal masses, m, separated by distance d, is F, then what will be the force? You know what? Let's write down Newton's law of universal gravitation. It's big G, M. It's M1, M2, but they told me both masses were identical, so I'm just going to write MM over D squared. So what's going to happen if we double the distance? First of all, where is distance? On the top or on the bottom in my equation? In the bottom. So if I make the bottom bigger, what happens to my answer? Smaller. By how much this time? Well, it's a d squared. So if I double the distance, let's write 4 times weaker. By the way, that there is called the inverse square law, and that's true of anything that radiates out. So see where Reed is right now? Everybody look at Reed. And see where Kyle is? Kyle's about halfway between Reed and myself. Kyle hears the sound 4 times stronger. Reed hears my voice 4 times weaker. And if we put someone 3 times further away than Kyle, he would hear me 9 times weaker, or 9 more times as quiet, depending on how you want to focus it. That's the inverse square law. Or if you're ever warming yourself by a fire, for example, if you're feeling too warm, if you double your distance from the fire is 4 times colder, not half as cold. Okay? Hey, what if we triple the distance? You know what? Let's put numbers in, because that way you guys can see the 4, which is 2 squared, and the 9, which is 3 squared. You can write it, but I just suddenly thought it's easier to spot. Hey, what if we quadruple the distance then? 16. It's still there. You could, I mean, the Earth's gravitational field goes out to the edge of the universe. It never hits 0. But once you go for a ways, it's so close to 0 that meh, you can ignore it. Hey, what if I double one of the masses? So now let's look at this. If I double one of the masses, that would put a 2, let's say, right there. Will that make the force bigger or smaller? Bigger. How many times bigger? Hey, what if I double both masses? as Zach says, the heavier it gets, the more attractive we find it, right? What if I cut the distance in half? So instead of twice as far away, I get twice as close. Now, when you get closer, will the force get stronger or weaker? Stronger, squared by how many times? Yeah, 4 times stronger, because you're dividing the distance by 2. What if we double both of the masses and we double the distance? Shaq, because doubling the masses makes it 4 times stronger, but doubling the distance makes it 4 times weaker. So if you're 4 times stronger and 4 times weaker, you're right. Stay the same. I'll probably, on your test, ask you some kind of a conceptual question like this. This will make a good multiple choice question. So I'll give you the equation and I'll say, suppose you blah, 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 blah. What happens to the force? Stays the same, 2 times stronger, 4 times stronger, 9 times stronger, all right, weaker, something like that. Easy to make it multiple choice.